I will start by reading and then I'm gonna explain the technique afterwards. So, integration by parts. We're looking for an integral that consists of two parts. Choosing which part is part 1 and which part is part 2 is crucial. Part 1 should be a function whose derivative is easy to find. For example, the derivative of x is 1. So this is how we locate part 1 and part 2. Part 1 is a function that is easy to differentiate. So if there's an x here, that's an easy function to differentiate. So it's in the right location. And part 2 should be a function that is easy to integrate. So if we look at this here and we see the legend on the right side, we can see that the integration by parts consists of two parts, and we need to identify which part should be part 1 and which part should be part 2. I'm naming them here f of x and g of x. And the result of this integration should be this way. Part 1 that I have chosen here, it's gonna remain as it is. I'm calling it here retaining it as it is. And this means integration, and this means like the derivation of the function. Then we multiply it by part 2, which is going to be integrated minus integration sign. This is the derivative of part 1, and then we multiply by the same part 2 here, which is the integration of part 2 into dx. And then you proceed with this part again until you find the final solution. This is in case it's indefinite integral, which is concept number 1. Concept number 2 I'm putting in this summary is definite integrals, which basically includes the limits of the integration. However, we do the same procedures. You see part 1 and part 2 here, and then I am basically substituting the limits into this part, and then I'm going to continue the integration with the parts in the question. In all the integration by parts, any question that is classified as integration by parts question is going to be one of those cases. Either concept 1, which is an indefinite integral, or concept 2 as a definite integral, or these following concepts, which are tabular integration, concept 3, and concept 4, which is the cyclic integration by parts. So you need to know which concept you are basically following for you to be able to find the final solution. I'm going to read the tabular integration and then I'm going to explain the technique. Concept 3, tabular integration. Tabular integration method is identified when one of the two functions have a higher order power, such as x to the power of 2, x squared, or x cubed, or x to the power n. So this is one of the two functions. As you can see here in the examples, one of the two functions, which is basically this one and this one and this one, has a higher order power, while the other function is a function that can't be simplified by differentiation. For example, an exponential or trigonometric function. These are trigonometric functions, and this one is an exponential function. And those functions can be simplified. Like if you find the derivative of cosine, it's going to be minus sine, or if you integrate cosine, it's going to be sine. The same for this one. If you integrate or differentiate e to the power of x, it's going to remain the same. Those can be simplified. In these situations, tabular integration is a more efficient method to solve the integral. And these are the examples. How it is done? It's done following this. Tabular integration simplifies repeated integration by parts by creating a table of derivatives. I'm highlighting the same color here. It means those are the derivatives, or those are part 1 that should be differentiated for one function and integrals for the other, alternating signs and multiplying diagonally to find the final answer. There is a method in which you put these in a table. You put the derivatives in one column, and in the second column you put the integrals, and you find the integrals in each row. You make one operation per row, and after that you multiply diagonally while alternating the signs. This is the method. And the last one is concept 4, which is cyclic integration by parts, double infinity integral. This is how I name it for you to easily memorize this concept. We sometimes encounter integrals involving two functions where neither can be simplified by differentiation. As we just talked about these, they can be simplified. For example, e to the power x, cosine and sine of x. In such cases, we apply integration by parts repeatedly until the integral takes a form similar to the original one in question. We can then move this repeated integral to the other side of the equation and solve for the final answer by combining like terms. So this is an example that is solved by double infinity integral concept. As you can see, both of these are infinity, or both of these that can't be simplified by differentiation or integration. And in this case, we understand this is concept 4, and we solve by integration by parts until we find an integral somewhere in the solution that looks like the integral in the question, and then we combine them, like we move this term on the right side on the left side and we combine it. It might be added basically, and there are going to be two of these terms, and then we divide each side, and this is how we solve these kind of questions. Tip, I call it the double infinity integral because both parts are continue or can continue indefinitely with integration or differentiation without reducing the form. Now let's jump into some examples to better understand how to apply these concepts, and starting by example number 1. As you can see here, we are basically integrating x, multiplying it into cosine x with respect to dx. In this form, it's easy. We can easily identify that it's an indefinite integral. We don't have any limits. At the same time, it does not fall under this concept number 4, and we don't have a higher power for the x. This means the best way to do this is by following the first method. And let me pull the first method technique here. As you can see, we need to identify the function that is easy to differentiate, and we need to locate the function that is easy to integrate. And here I'm choosing x as part 1 and cosine x as part 2. And following this method here, we retain part 1. We put the equal sign as following. We retain part 1 as it is. We integrate part 2. Cosine, integration of cosine is sine x minus integration. We find the derivative of part 1 and again the integration of part 2 dx. Then we simplify, we put the equal sign, and then we simplify, we multiply these. And as you can see here, 1 is basically multiplied by sine x, so we're basically just integrating sine of x, and it's going to be minus cosine x. We put the bracket to keep everything organized. This is the sign for the whole term. This is the minus, and minus minus is going to give us plus, and plus c because it's indefinite integral. Indefinite integrals, we add the constant at the end. That's for concept number 1. Moving down, we have example for concept 2, which is definite integrals. As you can see here, we have the limits, and they are from 5 to 10. This means it's a definite integral, and we have an inverse of an exponential function, which is ln of x with respect to dx. Let me pull the technique so we have a reference for our application here for the technique. We need to identify which part is part 1 and which part is part 2. ln of x is a function that we know for sure its derivative, which is 1 over x. It's a well-known derivative. However, it's difficult for us to integrate ln of x. And for this reason, I'm going to locate part 1, or I'm going to locate ln of x as part 1. And at the same time, I don't have a function here, another function to call part 2. But we know for sure that we can multiply by 1. It doesn't affect the integration. It could be before or could be after. But I know the integration for 1 is x. It's an easy function to integrate. And at this stage, I have part 1 and part 2 ready for the integration, and I can literally just apply this technique here on the right side. Applying the technique, let me scroll down. We retain part 1 as it is, and then when we integrate part 2, which is going to be x, we have the limits that we can substitute into this in the next step, minus the integration again based on this rule here, or this method, from 5 to 10, and I have the derivative of ln of x, which is 1 over x, and again the integration of 1 is going to be x. Simplifying those terms and cancelling those terms, we have only 1 left, and the integration of 1 is x. Continuing and scrolling down here, I have ln of x multiplied by x, substituting those limits and integrating the 1, and we have it x and minus. Also substituting the limits here is going to give us around 9.979. That's the answer for this question. Okay, great. Let's move to example number 3. So example 3, which is basically covering concept number 3, tabular integration. Though we can solve this using concept number 1, which is the indefinite integral, for demonstration purposes, we're gonna use it, or we're gonna solve it using tabular integration. How we know it's a tabular integration? As we can read the integration, it's x squared multiplied by e to the power of x with respect to dx. Here x has a high order power. It could be 2 or 3 or 4 or even more. And this is how we identify part 1 to be this function that is easy to be differentiated, and this is the function that's easy to integrate. I'm putting the colors here because I basically located part 1 and part 2. I'm going to proceed with the tabular integration. And the tabular integration states that you need to choose the function that basically as part 1, which is the function that we have chosen, x squared, and for each row you need to perform one differentiation operation. From x squared, the derivative of this one is going to be 2x, and the derivative of 2x is going to be 2, and a constant is going to turn into a 0. And for part 2 and its integrals, as I'm saying here, gx, is going to be the same for this exponential function. Ex, integral of ex is ex, integral of this ex is ex, and then you multiply diagonally, starting with positive sign, and then you alternate after each row. This is how you find the final answer here. So if we multiply x squared by ex, you get the first term minus 2x ex plus 2 to the power of ex, 2 multiplied by e to the power of x plus c, because we don't have limits here. So that's for concept number 3. Moving into concept number 4, which is the last concept. I'm just gonna make sure all's good. Okay, so for example number 4, double infinity integral. This is how we identify that this falls under the concept number 4, because we have both of the functions are infinity functions, or functions that can be simplified. We can't simplify them by differentiation or integration. And we proceed using basically the concept number 4, doing the integration by parts as we usually do, and we continue with the steps as we can see here. This is the retaining part 1, integrating part 2. It's basically the concept number 1. We are applying it again and again and again until you reach a step in which you find a term that looks like the term in the question, which is the integral of ex multiplied by cosine x with respect to dx. Here we have a minus sign, and we are able to move this to the left side, as you can see here, and then we're gonna have 2, like there's supposed to be 2 here. However, I simplified the solution, and I divided 2 by 2 on both sides, and this is how I got the final result. So there was a 2 here, and I divided by 2, and I got, this is the final answer, e to the power x sine x plus e to the power x cosine x over 2 plus c. That's the end of the lesson. I hope you liked it. I hope it was helpful for you to understand the concepts. Please check the links below that cover the rest of the topics. I have summaries on Gumroad, and I'm trying to post some videos from time to time that cover other techniques. Please leave a comment, or please leave questions in the comment section if you have any questions. Thanks very much, and take care. If you click on the first Gumroad link below, it will take you to my homepage on Gumroad. Gumroad is a well-known site for digital products, and here I'm listing all the integration topic summaries. Each summary includes examples that explain the main concepts. And if you scroll down, you will see a guide to selecting integration techniques. This is one of the interesting summaries because basically it gives you the bigger picture whenever you are faced with a new integration, and it simplifies the mindset that you need to follow to find the right integration technique. Well, that's the end of my video. Please leave a comment if you have any questions, and thanks for watching.